Have you ever stopped to think about the most important, most produced, and probably most invisible object in human history? Well, today we're pulling back the curtain on the unsung hero that powers, well, literally every part of your digital life. You've probably never even heard its name. So I gotta ask you a question. What do you think is the single most important switch ever invented? Is it the light switch on your wall? The ignition in your car? Nope. The answer is something way smaller. And there are billions of them sitting right in front of you as we speak.
So here's our game plan. We're going to uncover what this switch is, figure out how it's built, and then get into the really elegant logic of how it actually works. We'll see exactly why it totally dominated the world of electronics, and finally, appreciate how it's powering your world right now. Okay, let's jump in.
All right, first up, let's define this thing. We're about to get to the heart of what this switch actually is and why it's the fundamental building block of everything, from your smartwatch to a massive supercomputer. It's called the CMOS Inverter. Now, I know that sounds a little technical, but let's break it down real quick. CMOS stands for complementary metal oxide semiconductor. The really important word in there, and you'll see why in a minute, is complementary. It's just a tiny circuit made from two different types of transistors, a PMOS and an NMOS, that work together as a team. And its entire job, its whole purpose for existing, is actually incredibly simple. It performs what's called a logical NOT operation. In the digital world of ones and zeros, that just means it flips the signal. So if you give it a high signal, a 1, it spits out a low signal, a 0. Give it a 0, and out comes a 1. That's it. It's just a flipper, an inverter. So how do you actually make one of these? That brings us to part 2, building the perfect switch. And you're going to be amazed at just how simple and, frankly, beautiful the design of this world-changing component really is. Imagine we're building it right now. Okay, first you start with your power source. You connect one type of transistor, the PMOS, right to it. Then, right underneath that, you connect the other type, the NMOS. That one gets hooked up to ground. Now, the input signal? You send that to both transistors at the exact same time. And the output? You just grab that from the point right in between them. See? It's a really clean, simple, and perfectly symmetrical design. Okay, now for the magic trick. Section 3, the logic of the flip. So we've built the thing, but how does this structure actually do the flipping? This is where that word I told you to remember, complementary, becomes the star of the show. Check this out. The two transistors act like a perfect team, but in opposite ways. When your input is low, a 0, the top PMOS transistor switches on, while the bottom NMOS transistor switches off. This opens up a direct path from the power to the output, so the output becomes high, a 1. Now watch what happens when we flip the input. When the input is high, a 1, the exact opposite happens. The PMOS turns off, the NMOS turns on, and now the output is connected directly to ground. It becomes low, a 0. They work in perfect opposition. It's kind of like a seesaw. One is always up when the other is down. And this right here is the whole story in a nutshell. It's called a truth table, and it's the simplest summary of what this amazing little inverter does. If the input is a 0, you get a 1. If the input is a 1, you get a 0. Simple as that. Mission accomplished. Every single time. Okay, so it's a simple switch. Big deal, right? So why is this specific design, the CMOS inverter, the one that completely took over the world? Let's find out. Time for section 4, why it won the race. So, the CMOS design has some killer advantages. It's got high noise immunity, which means it doesn't get confused by stray electrical signals. It's also incredibly fast at flipping back and forth. And it gives you a really clean, strong output signal. But honestly, one of these advantages is the real MVP. It's the absolute game changer. And here it is, the superpower. The most critical feature is this. When the inverter is just sitting there holding a steady 1 or a steady 0, it uses almost no power at all. Remember how one transistor is always off? That means there's no direct path from the power source to ground for electricity to leak out and be wasted. Power is only really used for that tiny instant when it's actively flipping states. And why is that such a big deal? Well, this right here is the secret sauce of modern mobile computing. It's the reason billions of these switches can be crammed into your phone's processor without it overheating, and it's the reason your battery can last all day instead of just, 5 minutes. Low static power isn't just a feature, it's the superpower that makes our modern world possible. And that brings us to our final section,
powering your world. Let's just take a step back and really appreciate the mind-boggling scale of what this tiny little switch has enabled for all of us.
So, where are these things? The short answer? They are literally everywhere. They are the fundamental atoms of all digital logic. You'll find billions of them at the very core of microprocessors, memory chips, and even the timed oscillators that act as the steady heartbeat for all your electronics. If a device thinks, it's absolutely jam-packed with these inverters.
And hey, you don't have to take my word for it. In the world of chip design, it is known far and wide as the most essential logic gate. It's the absolute backbone of something called very large-scale integration, or VLSI. And that's just the fancy term for the entire science of figuring out how to cram billions and billions of these tiny switches onto a single sliver of silicone.
So the next time you pick up your phone or sit down at your computer, just take a second to picture it. Billions of these tiny, perfect, complementary switches, all flipping signals back and forth trillions of times every single second, and doing it while wasting almost no power. All of them working together, that's what creates the entire digital reality that we now live in.
It's a pretty incredible thought, isn't it? The elegant simplicity of this one little component, repeated billions of times over, gave us the modern world. Which really just leaves us with one final question to chew on. This tiny switch built our world. What's going to build the next one?